Good morning, everyone. Today we will be presenting our project on the topic of passive country houses in Germany. These will be the contents that we are going to go over today. We will start by presenting the topic of our research. This study examines the impact of the rapid economic expansion and modernization on fossil fuel demands, particularly in the construction sector. It highlights passive design concepts for cost-effective, environmentally sustainable buildings, referencing the first passive house in Germany in 1991. In regard to the literature review sector of this presentation, we conducted an extensive analysis of a wide range of studies on this subject of passive housing and its advantages and disadvantages. However, to provide a brief summary, we have included that we believe to be the four most relevant papers to our research. For the methodology of this study, we created a 3D model of a spacious family house with four master bedrooms, guest rooms, and a farm. It was then plugged into Open Studio simulation to calculate energy consumption. Afterwards, 7 passive heating and cooling strategies were implemented, and energy consumptions were compared to determine the most effective passive solutions for optimum reduction. Here we analyze the site where our passive house will be located. We assessed multiple elements such as climate, sun path, and its precious geographical locations. Our passive country house, located in Heidenau, Germany, features a comfortable climate regardless of the season, with a mild temperature and moderate rainfall. Furthermore, we assessed the sun path at the location during the summer and winter solstices, as shown in the image on this slide. In the base case, the total site energy was calculated for a north-oriented buildings with 1 by 2 meter windows, revealing cooling load peaking in June and July by 0.87 thousand British thermal units and heating load maximum in January and December by around 9,000 British thermal units and minimum in July by 0.04 British thermal units. The first scenario changed the orientation of the country house, thus it has resulted in a reduction of the cooling loads in July to 0.77 million British thermal units and a decrease in the heating loads in January and December to about 8.9 and 8.7 million British thermal units respectively. As a result, the overall energy usage of the site decreases from 79,300 British thermal units in the base case to around 77,700 British thermal units in this first scenario, which is optimal reduction. The second scenario added a thermal wall mass with an R value of 9.6 and increased the cooling load to around 4.3 million British thermal units in July and decreased the heating load by about 3 degrees in January and December, resulting in a significant reduction in a total energy consumptions from again 79,300,000 British thermal units in the base case to around 69,500 British thermal units in this case. The third scenario created a sunroom in the northwest corner of the house with a glasses of 8 by 4 by 2 of pond meter of 5.2 U value. This scenario is one of the least effective scenarios, increasing total energy consumptions to around 95,000 British thermal units, despite reducing summer cooling load by 1.44 million British thermal units. It is significantly increased the heating load to around 7.5 million British thermal units in January and December.
In the fourth scenario, we've played with the window size and type. We've reduced the window size to 1.5 by half meter and the type to be 6 millimeter clear windows of a U value of 40. This had a significant impact on the cooling load, which has been reduced to almost 1,500 kilo British thermal unit, and the heating to 47,000. In the fifth scenario, we have increased the window size to 2 by 3 windows, and we've added a few extra windows on the stairwell. This has significantly increased both the heating and cooling load. The heating was almost 64,000 kilo BTU, and the cooling also to almost 10,000 K BTU, thus concluding that this scenario is probably the worst of all the scenarios. Looking at all those previous scenarios and modifications that we have made, we have reached to a conclusion that the best optimal option to go with is to have the orientation of the building, the original orientation of the building, with the smaller windows, 0.5 by 2 meters, with the U value of 7.2. So in the sixth scenario, we've decided to add a further modification and to have an overhanging shading devices. This has resulted in a minor improvement in the total energy consumption, specifically the heating and cooling load. The heating was almost 74,000 kBTU, and the cooling reduced to 1,200 kBTU. In the seventh scenario, we've decided to add an extra measure. So we've oriented the building at its original orientation. We have the smaller windows, the 0.5 by 2 sized windows with the U value of 7.2 and 0.4 solar heat gain coefficient. So we've and the overhang shading. So we have modified the construction of the construction material of the building to be and we use the thermal wall, typical insulated wood framed exterior wall with an R value of 19.6. The original thermal wall was typical insulated steel frame exterior wall. This has significantly reduced the cooling and heating load, giving us almost the optimal scenario. The cooling almost 1000 kBTU, the heating to 42 kBTU, and the total energy consumption of the building to around 66,000 kBTU, which gives us the optimal scenario so far. So that being said, we have compared almost 8 simulations using Open Studio program with alterations and modifications within the program, orienting the building using different window sizes, using fixed and operable windows, adding shading devices to the windows, changing the window material and the thermal wall insulation material to try and reach to the optimal solution that will save energy. So that being said, the worst strategy that we have used was in scenario number 5, where all the windows have changed to 2 meter by 3 meter, which have increased the energy demand significantly to almost 100,000 kBTU for both the cooling and the heating loads. And then the best passive strategy for the country house that we have used was scenario number 7, when we used smaller windows with U value of 7.2, adding overhang shading depending on the orientation of the sun, where the sun, the facade that has the most windows is almost the east and the east facade. This has significantly reduced the energy, resulting in a minimal energy consumption within the building of almost 66,000 kBTU and a decreased cooling load to almost 42 kBTU. The heating load to almost 42 and the cooling load to 1000 K British thermal unit. To conclude our presentation, in this study we have examined the overall energy use of a full-size family country house in Heidenau, Germany. We have implemented 7 passive house strategies trying to control and simulate the energy demand of the building using Open Studio. We've multiplied different strategies and techniques. We've used smaller windows with a U value of 7.2, overhang shade and thermal wall of wooden frames. This has given us the optimal design for a building of that size in that area, resulting in almost a minimal energy consumption of around 66,000 kilo British thermal unit. And therefore, implementing this approach decreased the energy consumption by more than 13,000 BTU from the overall energy consumption of the site. Thank you very much for listening.